help with chapter 1. Maybe it's clear to you, maybe it's not, but this is your physics coach. Chapter 1 is visualize and sketch. I'll move you around just for a second. And when you visualize and sketch, you're going to show states or instants and label them 1, 2, 3. You're going to choose and show coordinates with a little arrow that says which direction's plus, right, left, up, down, whichever way you choose along a slope. And you're going to write variables with subscripts. And right now we're dealing with time, position, velocity, and acceleration will come in too. And that's it. And then we're going to look at the change. So you might say, I got a video for you in a second, a little bit. You might say, why are we doing this? And so there's a lot of complex motions within our body and our machines and so on. But Galileo, made a profound leap. People did things. They knew how to use levers and they needed how to pry things open and build things and do a lot of things. But why do things move the way they do? What's fundamental? And so Galileo, his profound achievement was actually to go simpler, things going along a straight line, up and down, sideways, along a ramp, up and down the ramp. And so too we will do that. Also, if you want to go to more complicated things, you need to start simple. So this is actually very profound, and it led to insights about the way things move that were contrary to what people thought. But it can be very intuitive. We're going to use we're going to look at change. So we're going to look at motion and then motion, things changing. And so today in this video, I want to talk about the Greek capital delta. It's a letter, it's pronounced D, like a D. It looks like a triangle too. And then there's this like squiggly D, little d, which is the lowercase delta. Sometimes we're not going to use that right here, but you can see that. And these are letters that are commonly used for change. So let's take a look at that. And in this chapter, really important, we're not going to do any calculations, okay? But don't expect to do calculations. We're going to calculate the change in time, change in position, and then there's a couple of places where I have you see if you can do it in your head. Okay, and that's what I'm going to do. This is a fairly short video. Let's speaking of short video, interesting thing about this Transformers video clip I got off of YouTube. Right, that car is moving. You can almost see it because of the blur. Now the time over here says 0.01. It could be 00. Right when the video starts, you can set that time as 0. You could set time wherever, but anything before that is not on the video. It's not what I'm analyzing. And you see this car right here is going in a straight line. And so, wow, it just went off. So I'm gonna go, I've got to go back and click that right now. Hold on. Right now we got lots of objects. And so we got to keep track of them and see who's going to catch whom and who's going to pass and who's going to do all that. If I pause it, you know that the object in the instant is not moving, but it is actually moving. That is, in the instant, its position will be in one place, and I can leave it paused like I did before. But you know that while its position can't change when it's paused at the instant, it is changing. The time won't change, but the time is changing. And so that's a conceptual thing that kind of messes with people, even though they don't realize it. Now we got things flying all around, projectiles, all kinds of stuff. But we're going to go back to the simple, and I'm going to turn that off. So let's take a look, and then I'm just going to show you some stuff, what this is about. First, I'm going to turn off that video. I should let you watch it. Okay, so if you want to design robots and you want to design things and all that, you got to know the basics of motion, why things move. And that was discovered by having a setup with kind of a simple equipment, simple setup. And so here I've got two carts and they can collide and I can add mass to one or the other and they could stick together and lots of stuff can happen. And by describing motion, I'll start being able to do more complicated things. Here, you have a set of ramps. And what we like to do in our class is say, okay, look at this one is kind of a straight incline or ramp. We often talk about the motion along a ramp. What if it's going down? What if it's coming up? Oh, it stopped. You know, what about friction? All that stuff. And these different shapes, if I put balls on these ramps, which one's going to reach the bottom first? And then you see what happens. Well, I didn't predict that. Might as well do it. And then the question is why? How can I think about it so that I am able to make that prediction? What is it about one versus the other? And there are a couple of ways to describe this. But here's the race. They arrive at different times. Why? And so we start by really understanding and describing motion. And that's what we're going to do today. By the way, there's, you know, it goes way beyond things moving. To make a sound, I mean, so it's not too annoying. Those things are going back and forth. They're moving. And if I pause it, they're still. But in reality, they're moving because I'm just pausing a video. So when I pause it, there's a certain instant. One other real quick thing. Look, I can take rotating motion and I can make linear back and forth motion. This has applications all over the place and in the human body and lots of things. So it's worthy and you become powerful at it because it's really in the details. So let's give this a shot. And I'll try to, we've talked about that. So real quick, it's not going to be hard, but you know, some of this might be confusing. Make sure that you use the end of chapter solutions that you'll find just by grabbing the yellow part. Yellow part, and you'll see pictures. And you can try to model those. It's okay to cheat. You're just learning. How do I label things really carefully? So look at that. So let me just show you this. Let's talk about time first. So time. For time, we have instants, or I'm going to call them states. Well, let me say an instant of time. Then an interval. Which is a change. Let me show you just a few quick examples. So in general, I can say T earlier. There's an earlier time in the video. And we abbreviate things because we don't want to write that all the time. And T later. So there's an earlier and later time in the video or in the process that we're analyzing. And so in general, if I want to write a general relationship that you can apply to any two states, one earlier, one later, then what I do is I say delta T earlier to later is equal to, we could even say is defined as, third line means defined as, but I can calculate this, the later time minus the earlier time. There's an equation. And later it's surprisingly powerful because you can manipulate this. And we'll get into the algebra later. But you could say, what's the later time equal to? Well, if you solve for it, it's equal to the earlier time plus the change. Or I might want an equation. I can move it around algebraically, chapter 4. The earlier time is whatever I end up with minus the change. And you can see that algebraically, but we're really not going to do that here. But this is actually a useful thing to do. Sometimes you'll get the change in your head. Let's try some examples. Let me put the specific examples in black. T1 equals. Let's be easy about it. Let's just use. Don't worry about significant figures until chapter 2. So T1, well, let's call that 0. Now, some people will use T0. I don't like that because that is a state. Some people use T initial. That's really weak. So we're going to go T1. It doesn't have to start at 0, but in our video it did. It's fine. T2. Let's do 2 seconds. That S is seconds. We don't write sec, we just S. Now, I could do any interval of time, any amount of time between my states. But here I'm going to do what's called a strobe, meaning the light goes on and it stops. The light goes on in equal amounts of time, equal intervals. If that's true, then T3 would be 4 seconds. T4 would be 6 seconds, and so on. So let's just take that. So if I wanted to know, for example, the time between 1 to 2, I can see it. The answer's there, but it's important to be able to write it. And so we do simple problems that you might be able to do in your head, but use it as an exercise so you can do more complicated. So I know that that's T2 minus T1. That's 2 seconds minus 0. Oh, it's 2 seconds. You knew that all the time. Yes, that's true. I could do from 2 to 3. Or I could do from 1 to 3, like I just wrote. 1 to 3. Then the later would be 3. The earlier would be 1. If these weren't nice integer numbers, be a little harder. So at 3, I got 4 seconds. Minus 0 is 4 seconds. Pause, and then I'll be moving, but in your pause, I won't. Let's go from, let's change this. Let's go from 2 to 3. I can't go 4 to 3 because the earlier is always got to be here. And then it's later, and it's earlier. And then, of course, I look at this. I know the answer because T3 is 4 seconds minus T2 is 2 seconds. And I know it's 2 seconds, fine. But again, if it's not nice numbers, you can't do it in your head. So maybe we don't want to make mistakes. And you can do anything. You can do from 3 to 4, from 2 to 4, from 1 to 4. You can do from 1 to 2, 1 to 3. And that's how you do it. So you can do that calculation, or you can just label it. So if you have a process, and I don't know what's going on, and it could go any which way. I like to go like 1, maybe that's 2, maybe that's 3. Now you haven't told me anything, so I don't know what's going on. It went from here to here. I don't know what happened in between. If you just show me those pictures, I go, I don't know what happened in between, but I can go T1, T2, T3. And that's what we're doing in this chapter. Now there's also position. And if you were here, I'd say, is that okay? Is there you have a question? Just ask me if you do. But before I do position, I want to do another example and take these and say, suppose T2 is, let's do 2 seconds again. But now T3 is whatever. T3 is 5 seconds. So you can see delta T is 2 seconds here, delta T is 3 seconds here, and delta T is I don't know, 1 second here. Why? Because maybe something is happening that you want to look at those times. So that's not a strobe process here or sequence here. And you can see it, delta t 1 to 2, 2 seconds, delta t 1 to 3, 5 seconds, 6 seconds, 1 to 4, 3 to 4, 1 second, 2 to 3, 3 seconds. And you could write it out exactly the same way. So that's not a strobe. So sometimes a strobe is nice for the following reason. If you tell me that there's an equal amount of time from here to here, delta t 1 to 2, and here, delta t 2 to 3, if I say that's the same amount of time, maybe 2 seconds or 1.93 seconds or whatever, that's the same time. And if you tell me that this thing doesn't turn around, it just goes in a straight line, never goes backwards, then I know that it's got to be going faster because it went farther. I can see it only because it's a strobe. If it's not a strobe, maybe this is longer and that's why it went farther. So these are the things. This chapter really teaches you to think about physics and to use super good notation. So I know that. If I flip it around, and now I say, this is 1, this is 2, this is 3, T1, T2, T3. Again, I don't know. You have to first tell me it's moving in a straight line and never turning around. So it can't do any funny things like this. It's got to go like this and then go like this. And if you tell me that delta t 1 to 2 from here to here is equal to delta t 2 to 3, the same amount of time from here to here as here to here, but you went less distance, I know the car must be braking or the person must be slowing down, whatever the case is. So that's what's nice about strobe. If it's equal, I can kind of see from these motion diagrams. They're not graphs. This is not a graph. We're not graphing anything either. I should say in this chapter, no graphs, no graphs, no graphs. Just really drill that in. It's easy to fall into it. So, okay, we're doing motion diagrams and we're labeling them. Super useful. I can't even train your thinking and your awareness. I also want to say something here, and that is a lot of people unconsciously, and it's fine, we make these mistakes, it's natural, so think that V1 is 0. I don't know. I don't know what V1 is. You saw in the video, that car was moving at t equals 0. You don't have to call that 0, but you can. And so if it's going this way, maybe it's traveling, maybe it's going V1. And if it's slowing down, then I'll make this a little shorter, V2. And maybe it stops, maybe V3 is 0. Or maybe it's just going a little slower, V3, a little smaller arrow, saying it's going that way. I can see just by, roughly, I made the longer arrow for faster, slower, and slower. If I went the other way, it'd be going faster and faster. Hope that's clear. You can pause and rewind. Okay. But once you get this, that's what these exercises are, just a whole bunch of situations where you do this and get the hang of it at something big. It's not, it's totally doable, but it's powerful. So I want you to know that. Now, what do I have? I've got time, I got velocity. What about position? Position, all right, fine. Now I need some positions. Let's at each one of these places, and you can make a list here. I could say X3, X2, X1. Now remember, let's get rid of this. Some things are not going to be known, but it's valuable to define them as a variable that you may solve for with algebra, things like that in chapter 3 and 4, algebra graphs, not motion. So I got time, position, velocity. I've got change in time. I can also get change in position. Okay. Sure, I could choose this to be 0. I don't have to. And then this is whatever. And I might know some things. That's the way these puzzles work. You'll be given some stuff and you find the other stuff with the tools, with the methods, with the training. So we're done with time. It's really that easy. This is a general, if you want to write a general formula, boom, and now I can apply it to any number of states and situations. Now I'm going to change this to space or position. Let's just call it space for now. And instance states, it's not an instant of time, it's a position. You have a certain position. And the interval in space is called the displacement. Instead of t, we can use usually x for one dimension often, but y often for vertical. Sometimes x for going along an inclined ramp. In 2 dimensions, you often use x and y, but you sometimes need 3 dimensions, x, y, and z. No big deal. Lowercase, don't use capital T. So the details matter because then we know what we're talking about. This is not t. I'll use x, but you'll see y and all that later. So x earlier is just xe. The position later is xl. The change is xl minus xe. That's a different idea. This is called displacement. This is position. I get rid of my t's. And I make those x1, x2, x3, x4. Oops, make it a subscript. So don't put it there, put it down here. I'm sure it's a subscript. We just choose that. Can't be seconds. That doesn't make sense. Okay. Let's just talk about this process. We're not doing time. We can do time. We can do position. Velocity, acceleration. Acceleration won't really be changing, not at the beginning. So I can give anything. Notice that I can set x equal to 0 anywhere. It doesn't matter. It doesn't change anything. I can say the position of this is 0 or the position of this is 0. It doesn't matter. If you're consistent, you're going to be able to describe the process. So x1 equals 0, maybe. And then x2 and x3, is this going positive? Let's think about a number line. If this is positive, and if this is 0, don't really need units when it's 0. If this is 2 meters, a meter is this far, long step, it's this much. That's a meter. So for me, it's like that. For you, it might be different. And then this would be, let's just make it easy, 1 meter. Wait, that's not true. You should see that and go, wait, what are you talking about? That's wrong. Oh, maybe what I was talking about is the delta x is 1 meter. It's still farther away from, so that's 3 meters. Oh, okay. I think about it. This will help you think about it because it's too much stuff. You're going to make mistakes, but you'll correct yourself quickly with this. Okay, I could say that. The minute I'd say, no, you know what? I want this to be positive x because I'm used to right being positive. then I have to add a negative sign because it's in the negative direction, that position, negative direction. You'll get to play with that a bunch in the exercises, but just so you see it. So I need to show this so that I don't mess up and so that anybody following my work will know what I'm talking about. That's true, that better be negative. If positive's that way, then they're positive. Just be consistent. Now, again, let's just say, and then we'll do a few things and then we're done. So short exercise. Let me say that let's make this positive X direction is that way. Just showing you where my positive is. What if I call this 0? Why? I don't know. I have to have some reason. Maybe we're told to. Maybe that's part of the exercise. And maybe, let me show you this. Delta X, well, let's just go, let me get this. Maybe this is negative 2 meters. That means 2 meters to the right. The right is negative here. And maybe this is positive 1 meter. You can do that. It doesn't matter. Just let go of all that stuff. And then I can do things like this. I can go, oh, let me check this out. Here's the motion. Here's how I'm choosing to label it. And then some times. So what's the displacement? Well, displacement in this case has to be earlier to later. I can't go from 2 to 1. And you could measure, but there's a process. It's a movie. It's a car. It's a transformer. You're moving from here and then to here and then to here. And sometimes we'll go backwards. Then here, you have to think of that motion. And so I've got to go from earlier 1 to 2. And I know what that's defined as. That's X later minus X earlier. Watch what happens. Very easy to make negative sign or minus sign errors. We do it all the time, all of us. And we catch ourselves if we have good techniques. We catch it real quickly. X2 is 0 minus X1 is, now here's what I encourage you to do, minus 2. Minus a minus 2 is plus 2 meters. And notice that when I went from 1 to 2, or when this thing did, delta X 1 to 2 is in the direction I called positive. And it is 2 meters in the positive direction. And the math worked that out. Just a little bit. It doesn't get too much more complicated than the stuff that we're going to do here. And so it works. And then, of course, 2 to 3 is going to be plus 1 meter. Let's try 1 to 3. 1 to 3. Later is 3, 1. 3 is plus 1 meter minus X1, which is negative. That's 1 minus or plus 2. Oh, that's plus 3. And delta X, 1 to 3, is in the positive direction, 3 meters. We can write it out, we can see it, and so on. So those are the only kind of calculus, but it's very useful because, as I say, you can actually move that equation around, and hard stuff can get simple. If I take this and I throw in a fourth state, it could be anywhere. It's kind of messy over here. So let me put it just 1 meter over here. And by labeling the states 1, 2, 3, 4, I know that you're just showing me snapshots. You're not showing me the video, but I know the video, as long as nothing funny is going on, which we're not going to do that to you. Then it goes from here to here to here. If it's still moving, it had to come here and stop somewhere, and I might have chosen that as a state. Or I didn't, I don't know. Whatever, just go with the description and make some mistakes. And then it's got to come back here. It can't go from 1 to 4. It's physically the video, you're describing the video, describing the transformer. I don't know, maybe there it stopped. Who knows? Maybe V4 equals 0. Whatever. There's lots, you can imagine all the examples. And then I would say X4 is equal to, if that's another 2 meters, -3. Now watch this. This is the last little thing that I want to show you, and then hopefully the examples and everything will get it. So delta x1 to 2 is from here to here. That way, I call that positive. 1 to 3, from here to here. That way, I call it positive. 2 to 3, from here to here. That way, I call it positive. This one's the easier one. 3 to 4, from, let's get rid of all this stuff. 3 to 4, from here to here, I call that negative. It better be negative. Let's calculate it. And then, hold on, one last little bit. What do I want? I'm going to get 3 to 4 is 4 minus 3. X4 is -3 meters minus X3 is 1 meter. -4 meters. 1, 2, that makes 3, and 4 in the negative direction. So these puzzles start getting more complicated, and just like a bunch of puzzle pieces on a table, you can't do it in your head, and you shouldn't, because you want to work your way up to more complicated stuff. When you break it down like this, that's why people do these puzzles, and a lot of people, oh, you're a genius, you could do it. It's like, no, I just take one little step at a time. And I practiced. Now watch this. This one's interesting. So that's delta x, or the displacement from 3 to 4. Two things. As far as distance goes, which I write as a separate thing, I say distance from earlier to later. There isn't really an equation for that. You have to kind of add it up. And if I know, I've got to know the video. If this one moved like this, okay, I moved 2 meters and kept moving another 3 meters. And then I went back another 4 meters. So the distance is 2 plus 1 is 3 plus 4 is 7 meters. To go from 1 to 4, my distance, the distance you add up, the whole motion. But the displacement, let's do 1 to 4 displacement. 1 to 4, that's 4 minus 1. 4 is -3. 1, we called -2 because we're just messing around. -2 meters, you don't do that, you're going to make a mistake. And let's just, writing out a little bit to be careful is always worth it. -3 meters plus 2 meters, -3 plus 2 equals -1 meter. And yes, even though for displacement, all that matters is where you started and where you ended, and I don't care how you got there, because that's the change from 1. Your change in position from 1 to 4, even though you did all this, is right there. And how much is that? That's this. But the process, this is the last thing I think I'm going to say. The distance traveled along the path, we added it up, was 7 meters. And negative doesn't get subtracted because distance is distance. You can't like drive south. If you call north positive and then you drive south, it's not like traveling negative distance. Then your gas tank would fill back up. Oh, I'm traveling negative distance, so you must be using negative gas or electricity if you have electric. That's all there is to it. Do some and then get used to it. That's huge. Too many people are confused by this. That's the delta notation. That's the earlier to later, and then specifically putting in numbers in the process. And then if you have two objects like a Camaro and a transformer or whatever, or a dog chasing a cat or cat chasing a dog or whatever, you can do this. And it goes a long ways. As you saw, Galileo went a long ways, as often called the father of modern science, because of breaking it down like this. Time, position, time, change in time. Position, change in position, called displacement. Also distance. Velocity. And then acceleration we'll get to, so not for now. And I hope that makes it a little clearer. Use the solutions in the back, and that's it. Reach out for help when you need it.